This presentation is for a geothermal standing column residential heat pump system in Mason, New Hampshire. It consists of a single vertical well which supplies the geothermal heat pump and domestic water. It has a forced hot air heating system. The heat pump also preheats domestic hot water and also provides cooling in the summer. This virtual tour consists of 3 parts. The first part is how a heat pump works. Second part is the tour of the actual system. And the third part is some additional information regarding alternative types of geothermal systems. Part 1. How a geothermal heat pump works. In southern New Hampshire, bedrock and groundwater temperatures below 30 feet are a near constant 50 degrees Fahrenheit. This, quote, heat is extracted and transferred to a home's heating system. This is a sketch of a standing column well showing the basic operating principles. In geothermal terms, it's also known as an open loop system. For this system to operate efficiently, it needs a deep well between 250 to 500 feet deep to maintain sufficient heat transfer between the ground and water. It may need to be deeper in some cases due to high heating demands in cold climates or high cooling demands in hot climates. It must be designed to be impervious to drought conditions. If the well isn't deep enough, as heat is extracted, the return water can be chilled such to render the system ineffective. Likewise, it can be overheated in summer cooling situations. And in some other regions of the country, this well may be up to 1,500 feet deep, depending on soil and water conditions. The pump intake is at the bottom. The return discharge is near the top. The warmed or cooled discharge water, depending on season, remixes with the standing column water and is thermally brought back to ground temperature by the surrounding bedrock. In extreme heating or cooling conditions, the bleed part removes about 10% of the discharge from the well. This reduces the temperature effect of the discharge water by the pump drawing in additional ground temperature stabilized water from the aquifer. And note that using this well for domestic water aids in drawing in additional water from the aquifer and helps to maintain a steady 50 degrees Fahrenheit water temperature. In the Northeast, standing column wells are the norm due to bedrock being near to the surface. Bedrock transfers heat better than loose soils. They're cost-effective and efficient compared to other types of geothermal systems, but the water quality and quantity should be measured before any final design choices are made. The heat pump can be damaged from scaling by minerals in the water, acid or alkaline pH, incrustation by iron bacteria, or erosion by sediments. If near the ocean, salinity can be a factor. The water flow rate must be capable of supplying water and heating simultaneously. To be efficient, the well needs to be deep. The more surface area for heat transfer, the better, as there's sufficient quantity for maximum flows on cold and hot days, including domestic water use. And if the well is not deep enough in a drought-susceptible location, then it's certainly not going to work. This next group of about 15 slides goes through more technical details of how a heat pump transfers heat from one place to another, and also how the cooling aspect works. If you're not interested in these details, you can skip ahead. If you are interested, and you can always pause to study the slides more carefully. This is a diagram of an overly simplified heat pump in heating mode. The incoming groundwater at 50 degrees Fahrenheit transfers its heat to the refrigerant in the lower heat exchanger, which evaporates the refrigerant into a gas. The outgoing water exits at a slightly lower temperature. The refrigerant flows to the upper heat exchanger, exchanges its heat to the incoming cool air from the house, and condenses to a liquid. This is a more detailed view of how the refrigerant transfers heat. First, the incoming groundwater transfers its heat to the refrigerant and the lower heat exchanger. Second, the liquid refrigerant is heated and evaporates into a cool gas. The reversing valve directs the cool gas to the suction side of the compressor, which reduces its volume, thus heating it. Fourth, the hot gas is directed to the upper heat exchanger, where it heats returning cool air from the house. Fifth, the refrigerant condenses to a liquid and completes the cycle. Sixth, the thermal expansion valve allows the cool, high-pressure liquid from the condenser to expand to a cool, low-pressure liquid into the evaporator. It prevents liquid from entering the compressor and prevents superheating of the refrigerant by monitoring the evaporator temperature. Cooling mode. Next, we'll see how the refrigerant cycles through the two heat exchangers in the opposite direction from the heating mode. In this simplified drawing for the cooling mode, we'll see that the hot air from the house transfers its heat to the refrigerant in the upper heat exchanger, which evaporates the refrigerant into a gas. The refrigerant then flows to the lower heat exchanger, exchanges its heat to the water from the well, and condenses to a liquid. Notice that the well water is heated from the house air. This is a more detailed view of the geothermal heat pump in the cooling mode. First, the refrigerant absorbs heat from the house air and evaporates into a cool gas in the upper heat exchanger. Second, the reversing valve directs the cool gas to the suction side of the compressor, which again reduces its volume and heating it. Third, the hot gas is directed to the lower heat exchanger, where it heats incoming water from the well. The flowing groundwater is heated by the hot gas in the lower heat exchanger and exits back to the well. Fifth, the hot gas is cooled and condenses into a cool, high-pressure liquid in the condenser. Sixth, the thermal expansion valve allows the cool, high-pressure liquid to expand into a cool, low-pressure liquid and regulates the flow between the condenser and evaporator. It prevents liquid from entering the compressor, and it prevents superheating of the refrigerant by monitoring the evaporator temperature. Part 2. Virtual tour of the actual system. A single well supplies domestic cold water and supplies ground temperature water for the heat pump. This view shows the connections through the basement wall to the well. The incoming water for the house is the black steel pipe, which leads to the pump pressure sensor and pressure tank. The heat pump is fed by the vertical copper pipe, and the returning water to the well is through the gray PVC. This is the constant pressure controller. It controls the pump at the bottom of the well. It electrically maintains a constant pressure in the system by adjusting the pump motor speed. It avoids the low and high pressure swings of typical on-off pumps and allows for use of a smaller pressure tank. It is also more efficient by its ability to maintain low flows at low pump speeds. It also has lots of other useful features to protect the pump from the soften startup currents. The incoming water from the well enters on the right in this view, passes through the sediment filter, pressure regulator, pressure gauge, and a control valve before flowing to the heat pump on the bottom PVC pipe. Combination of the pump maintaining a certain force in the system and the setting of the pressure regulator to account for all the pressure drops in the system for peak performance of the heat pump system. The water lines from the well to the heat pump and back again are leveled to eliminate unnecessary pressure changes. Here it is, a Climate Master geothermal heat pump. On the outside, it looks very similar to a furnace. It's got lots of bells and whistles, in addition to the standard components of the water to refrigerant heat exchanger a compressor, and a refrigerant to air heat exchanger for the forced hot air heating system. And as explained previously, the refrigerant loop can be reversed to provide cooling in the summer. It has a heating loop to preheat the domestic hot water supply when excess heat energy is available. Those are the vertical lines for the pipe insulation. This is a two-stage compressor which allows operating more efficiently when at lower heating capacities, and it has an electronically commutated motor that varies the speed of the blower fan to match the heat exchanger performance. It also has a modulating water valve that varies the water flow from the well based on the incoming water temperature and temperature drop across the heat exchanger. This reduces unnecessary water usage. These photos show the internal views of the geothermal unit. On the left top is the air filter and the refrigerant to air heat exchanger, and in this cutaway view that's reversed from the actual unit. On the lower section there are views of the coaxial tube water to refrigerant heat exchanger and the two-stage scroll compressor. These views show the details of a typical coaxial tube heat exchanger. For open loop well water, it is made of copper nickel, which resists corrosion and mineral deposits. The water flows in the center of the convoluted tube, and the refrigerant flows along the periphery. The entire unit is then insulated. There are temperature sensors for incoming and outgoing geothermal water, and also the compressor discharge line. There are two refrigerant line sensors. There's an outgoing air sensor, and there's a sensor on the incoming domestic hot water. All of this is computer monitored, and flows are adjusted to meet demand and maximize efficiency, and to prevent overworking the well or the heat pump. The domestic electric hot water tank is a seamless polybutene tank that will not corrode. The cold water feed line is routed through the heat pump prior to coming to this tank. Larger two-stage tanks are recommended to take advantage of the essentially free excess heat from cooling in the summer months and to lessen the installation costs on a per-gallon basis. This view shows the return flow to the well through the gray PVC pipes with the red arrows. The orange top device is a back pressure relief valve acting as a pressure reducer. It stays closed to maintain water above a certain pressure in the heat exchanger. When the pressure exceeds its set point, it opens and allows water to flow back to the well. It also prevents the column of water going back down the well from siphoning off water and creating a vacuum within the heat exchanger. The outgoing flow is split prior to the pressure reducer. The upward flow is to a drain shown in the next slide. This is a view of the discharge bleed. This piping leads to the external perimeter drain. This is useful when the heated discharge water in the summer will overheat the well water, or the cooled water in the winter will overly chill it. Using this drain to bleed off a small percentage of the returning water keeps the well water at a more desirable constant ground temperature. It makes the heat pump run more efficiently. Typically, temperature monitors will control this when discharge temperatures are below 40 or above 85 degrees Fahrenheit. A few random tidbits. This house is a wood stove as a backup heat source. The geothermal heat pump is a major advantage over an air source heat pump. Due to the consistent temperature of the geothermal heat source, it is typically 40% more efficient. Also, the geothermal unit does not require the frost cycle since it is not exposed to the extreme outside air temperatures. The geothermal unit being indoors has a longer lifespan due to less harsh environmental conditions. The only maintenance is to empty the sediment filter and change the air filter. There are no yearly service calls. Part 3. Alternative types of geothermal systems. Some alternative geothermal systems. Regarding open loops, instead of the single well providing inflow and outflow as shown in this virtual tour, separate wells can be used, or an open discharge without a second well. Note, some municipalities may prohibit open discharge. Regarding closed loop systems, instead of using groundwater directly into the heat pump, a closed piping system with an antifreeze mixture can be used, either looping vertically up and down wells or stretched horizontally below frost line in slinky type coils, or submerged near the bottom of a water body. This can eliminate future maintenance because this piping is sealed and pressurized. It is not subject to mineral or iron deposits, but has other construction expenses. Any and all of these options require expert help to design and build. They are not a do-it-yourself project. These photos are examples of vertical and horizontal ground loops for a closed system. The photo on the left shows two pipes joined together, which would be inserted down the vertical shaft of a drilled well. And the photo on the right is the coils of a horizontal loop system laid out underneath the frost line in the ground. Multiple closed loops can be used for additional heat transfer, either vertically or horizontally. Many thanks to the homeowner who sent in photos of their geothermal system for this virtual tour. Many thanks to Bosch and Climate Master for their very good manuals obtained online in the Department of Energy. There's a ton of information available on the internet, and this is just the tip of the iceberg as far as knowledge and variations of possibilities of how to do a geothermal heating system.